physical AI-based drug discovery. So he's a chemical engineer by training. He has a bachelor's from Caltech and his doctor from MIT. And he did a postdoc nearby the Broad Institute and then sort of returned to MIT, where he's currently an associate professor, I believe, class of 57, career development professor in that department. He is, again, really one of the pioneers at bringing together data and chemistry, right? So he's a chemist, so he has that intuition, but he also knows about data science and brings the two together in very usable, very practical ways. He's won numerous awards, and we're very happy to have him here today. Thanks, Connor.
Thanks, Joe. Yes, thanks, Severin, for inviting me in for the talk and for folks online as well. What I'm trying to talk about today is as the title suggests, tailoring generative AI to molecular design, because there's a lot of interest and excitement about generative AI across disciplines. But of course, chemistry offers some quirks, some challenges that might need a little bit of domain tailoring, as hopefully you'll be convinced about by the end of the talk. Obviously, AI is becoming really pervasive in our daily lives, in scientific domains as well, right? Or people are routinely using large language models, for day-to-day tasks, but we're also seeing the use of AI in sort of prolific scientific applications. And there's the high-profile examples like AlphaFold, and there's the slightly less high-profile examples, but still really interesting ones across different disciplines, right? Things including really large-scale climate and weather simulation, thinking about sort of energy optimization and more sort of operations research, as well as a lot of work in chemical synthesis. And so what unifies these many diverse applications of AI to me is the fact that it's just helping us navigate scientific discovery cycles, right? We're using AI to help us make sense of observations, to form hypotheses, and to drive then experimental design. And so in our group, we think about the intersection of AI and these techniques with chemistry. We think about a few different subfields of chemistry, first being synthetic organic. So how do we build models that understand how chemical reactions proceed, use that to engineer new synthetic pathways and preparations to molecules of interest. We think about the use of AI for medicinal chemistry and molecular design. So how do we find the chemical structures that have desirable properties, and how do we generate ones that are more optimal than the current ones that we're testing experimentally? And there's some work as well on analytical chemistry that I won't touch on at all today, but we're thinking about using AI for structure elucidation and applications like metabolomics. But yeah, the focus will be on more of the design aspect and focusing in particular on a couple of threads related to generative design in a way that makes these tools, again, much more practical for chemical sciences. So I'm increasingly definitive about working on small molecules. So there's a lot of excitement about other modalities, protein design, antibody design. We still like working with small organic molecules for their versatility. So they do still make up the majority of FDA-approved medicines. We use them in agriculture, we use them in material science, and even in defense. And even though we do see this sort of slight shift in the development of different therapeutics, small molecules have a lot of benefits that will persist as far as typically their shelf stability, right, manufacturing costs, ability to permeate the blood-brain barrier. Now, we think about different computational techniques to accelerate the discovery and identification of these kinds of structures. And we're going to really focus in on the setting where we're trying to design structures, given that we already have some sense of a structure-function relationship. So a cornerstone of computer-aided molecular design is the building of these structure-property relationships. Here it's shown as this really idealized cartoon surface. As you change molecular structure on the X and Y axes, you'll have better or worse properties on the Z-axis. And we can train these with supervised learning if we have labeled data sets. So for example, molecular structures and potencies. We can we can build these models using first principles approaches as well, especially if we're dealing with electronic structure calculations or with structure-based simulation techniques. Now, given that structure-function relationship, the question then becomes how to identify the structures that achieve some desired function. And so the first paradigm, like really classic paradigm, would be virtual screening. We simply take a long list of molecular structures for which we want to predict their properties, we predict their properties, and then we simply take the maximum from that set. And so we might work with these virtual screening collections, these virtual chemical libraries, and simply identify the best candidates from that list. And of course, now with generative techniques becoming increasingly prevalent, right, the idea right? The promise of them really is that we can take this understanding of the structure-function relationship and directly iterate our way to the top. So we can use these algorithms to more efficiently explore a chemical space and directly generate the structures that are thought to exhibit the kinds of properties we want. Now, these surfaces are intentionally sort of generic in terms of property. So this could be some on-target binding potency. It could be some particular, optical property. If we're working in that space, it could be other drug-like properties. The idea is the same, right? We have some understanding of the landscape between structure and function, and we want to navigate our search space of chemical space as efficiently as possible. Then the world of virtual screening, what's becoming more common is to use these make-on-demand libraries. So make-on-demand libraries are these virtual chemical spaces that are constructed, right, through the combinatorial application of reaction transformation rules to commercially available or in-stock building blocks, right? Simply put, a chemical vendor says, here's what I have in stock, I can sell you this. And then they think about the reactions they can run, and they enumerate them the millions or billions or trillions of compounds that they think are synthetically accessible to them using those building blocks. This has really been popularized by folks like Dianamine, also Wuxi, but there's been proprietary collections in pharma for decades, right, of these virtual make-on-demand libraries. Now, given that we have, this sort of enumerated chemical space of millions or billions of structures, even if we have relatively inexpensive simulation techniques, right, we're not really going to want to do billions of simulations. So one of the early stage, really coarse evaluation protocols that people use routinely in structure-based design is docking. Docking is not so expensive. Fast implementations might get you sort of a predicted affinity in a CPU seconds, being a little bit generous. But we still don't want to do that 100 million times in a brute force fashion. And so early on, sort of in the group, in a very simple way, we've just sort of inserted a model that's going to take some partially docked library of compounds, learn to predict the results of the docking calculation for untested compounds, and iterate. There's a very straightforward sort of insertion of model-guided optimization or Bayesian optimization into this otherwise exhaustive workflow. And the sort of iterative approach to docking is also something that part of Chirgasov has worked on quite a lot, and it's really remarkable, I think, how well it does work. It's not surprising that it works, but it was surprising to me how well it works. Okay, so if we're trying to take a large library, in this case of 100 billion structures, we essentially have this black box function that evaluates them. We can identify 90% of the best molecules in those top 50,000 structures, 50,000 compounds, with a fraction of the simulation cost. So a 40x reduction in computational cost to still get to the vast majority of the high-performing candidates. So we can simply replace these exhaustive high-throughput workflows with a little bit of model-guided optimization, and that helps us out quite a bit in terms of cost. It lets us explore then larger design spaces. Now, on top of this idea, there's a lot of sort of bells and whistles you can expand out. Sort of extended this to use more principal notions of uncertainty quantification, so that when we've identified a candidate structure as having a low likelihood of being a high-performing compound, we sort of exclude it from further consideration and save a lot of computational overhead. We've extended these in a fairly straightforward fashion to multi-objective optimization. So if you have multiple targets, maybe a target and an anti-target that you're docking to, you can also understand the trade-off between those. And pretty recently, we've been developing some new acquisition functions for this iterative Bayesian optimization that define diversity in a very particular way that lets us sort of construct more diverse batches of molecules and in some ways hedge our bets and decorrelate the risk that any one molecule in a batch is going to fail. So there's some interesting things we can talk about with this later if there's interest, but this is sort of summarizing a little bit about what we're thinking in the virtual screening case, where we can still use AI to accelerate the process. Now we get to generative design. So early on, right, the appeal of generative design for molecular structures was that we could repurpose language models and we could use file-strain representations to encode chemical structures. It's been established in cheminformatics. And we could simply use things like RNNs at the time, of course, evolving into all sorts of transformer-based generative models these days, to propose novel chemical structures through the generation of text. And the sort of idealized view of what this could unlock for molecular design is summarized pretty well by this figure that is now sort of fairly old and fairly optimistic from a colleague at MIT, really, for the sort of early SMILES BAE. Right? The idea was that you could encode a SMILES string, get into this numerical latent space, decode it back out, right? Train it as an autoencoder. But in this latent space, you could smoothly navigate this beautiful hill, right? You could climb that hill, maximize your property, decode the structure that achieves that maximal property. The thing is, we've all sort of realized some painful lessons, right? Latent spaces, when you train it like this, are not typically so smooth, right? The properties that we care about, like binding to a particular protein, they're not things that you can just climb a smooth hill and then decode your optimal binder. And so we've had a lot of deep generative design techniques in development since 2016 is when I'd say this really kicked off. There were generative approaches decades before, but deep generative approaches really emerged in 2016. We've still been sort of stuck in a state where the structures that we get out of these models aren't terribly synthetically tractable. We'll focus on that later. The algorithms for doing optimization aren't very sample efficient. So when you run these sort of iterative optimization loops, the models require tens or hundreds of thousands of attempts before they find molecules with good properties. In a realistic experimental campaign, you don't get 100,000 tries to find a good molecule. When we apply these algorithms to optimize things as simple as docking scores, they simply don't do that well empirically. And if you look at the quality of interactions of the ligands that they generate, they're not very good. They don't exhibit strong selective non-covalent interactions. And so we can't address all of these in one seminar. We're going to really focus, though, on two parts. The first being this issue of how do we get generative models to understand interactions with proteins? And then the second is how do we understand synthesizability and how do we integrate it with generative techniques? So there'll be sort of two main threads organizing the rest of the talk, again, starting with this exploration of molecular interactions being a primary consideration of how we want to design new molecules. So if we jump back to the virtual screening world just for a second, it's quite common to use shape-based screening techniques like rocks to do things like look for volumetric overlap and similarity between a query molecule and a database of reference molecules. And so this notion of using sort of shape and sometimes colored shape, if it's rocks colored, to understand what ligands or potential ligands are structurally similar to one that have identified them. We apply this routinely in the virtual screening setting. And so first natural question to ask is if we're using shape as the basis of virtual screening, is there a way to shortcut that exhaustive screening approach and instead learn how to sample from a conditional distribution of molecular structures given a target shape? So the idea behind this model we're sort of seeking out to build is that we want to learn the distribution of molecules and their shapes so that we can sample, given a target shape, what are molecular structures that can achieve low energy conformations that approximately satisfy that volumetric shape. So it's a generative version of rocks for those who are very familiar with it. And so in this model that's called SQUID, a slightly forced acronym, we have sort of a dual encoder where we will equivariantly encode the shape of a molecule represented as a volumetric point cloud. We'll have a variational encoding of a molecular structure just using graph encoders, sort of fairly typical graphical networks. We sort of have them in a shared latent space, though. And so what we can do is we can then decode to regenerate that molecular structure. If we train this autoencoder up front. And when we generate the new molecular structures, we're going to choose to do so with a fragment-based generative approach where we sort of take a growing scaffold and we sort of select where to add a new fragment, we optimize the dihedral, and then we iterate. And so we have this way of encoding shape and structure and then decoding a new structure out to the other side. Now, the idea with this model is that we can then decouple molecular shape and molecular identity, or the molecular graph. And so what we can do is we can then take a reference molecule, we can generate a volumetric profile that it will exhibit, and we can sample a diverse range of chemical structures that approximately satisfy that shape. And so here, we're just looking on the bottom, right? The same blue mesh is being used as the query from the reference molecule, and you're seeing a variety of different chemical structures that approximately achieve that target three-dimensional shape. And even though the model does love amides because it's been trained on data sets that love amides, you do see a decent amount of chemical diversity as you sweep across this chemical series. We can actually tune, this heat map is showing, we can actually tune the trade-off between achieving high shape similarity, but also being chemically diverse, right? In case we wanted to explore a diverse set of chemical series. And so squid is very sort of useful for doing the shape generation. We can query the model with a whole bunch of different shapes, and these are actually conformations of the same reference molecular structure. And we can generate then novel ligands that will approximately encode the shape. This is sort of a first step for us into three-dimensional based molecular generation. Now, squid was nice, but it has two main limitations, I would say. The first limitation is that the way that we were generating structures was through autoregressive fragment-based decoding. So we had this sort of growing structure, we would just choose an attachment point, choose a fragment, find the dihedral, and iterate. And this is good at ensuring some geometric validity of the structure because we can fix bond angles and distances and only optimize dihedrals. The geometries we get are quite reasonable, but it's really clunky. It's a very sort of clunky way, just a purely difficult to train kind of way of generating structures in 3 dimensions. Limitation 2 is that, of course, shape is really not the end of the problem, right? Shape gets you part of the way to thinking about ligand design, but the interactions between small molecules and proteins are governed by significantly more than just some rigid volumetric shape. Right? There's some applications maybe where host-guest interactions are shape-driven, but here, shape is maybe the first step. Then we have to worry about electrostatic complementarity between a ligand and a pocket, as well as a whole range of different pharmacophoric interactions or non-covalent interactions. Right? At the atomistic level, how are these atoms in our ligand interacting with residues in a protein? Now, there's a wide range of these non-covalent interactions that are known to drive good selective binding events. There's a fantastic article about this. I really like this article. I always reread it and pick up something that I missed the first time. So Bad Chemist Guide to Molecular Interactions, and it really just sort of documents the wide range of interactions between ligands and proteins that are sort of responsible or at least attributed to causing these good selective binding events. So these non-covalent interactions are quite important. And as others in the field have quantified, the quality of ligands that are generated by current generative models, they don't sort of measure up to native ligands of proteins, right? Ones that are observed to bind strongly, ones that are observed in co-crystals of protein data bank. And so this benchmark post-check was a benchmark that did like a range of different 3D generative models whose job was to take a protein receptor, protein pocket, propose a new ligand. And they would take the generative pose, they would sort of relax it, rescore it, and analyze the kinds of interactions that were achieved. And they sort of do a lot of analysis, but just to sort of summarize it down to one plot, right? These two graphs are just showing the distributions of the number of hydrogen bond acceptors on the top and hydrogen bond donors on the bottom. Or on the far left, we have sort of native ligands and the cross-docked sort of benchmark sets, and all the other distributions are for 3D generative models. Right? And the punchline here is that you can see the plurality of ligands that they generate have 0 hydrogen bonding interactions with the receptor, which is not a good recipe for having good selective sort of on-target engagement. So this is sort of a challenge that we wanted to overcome, building on what we had already thought about with shape-based design. And so we revisited our original premise where we said, what if we could sample from shape conditions, or sorry, shape-based sort of conditioning? What if we extended that to not just be about shape, but to be about the kinds of interactions that we would want a ligand to achieve? So the idea here is that we want to say, okay, not just to query shape, but we want to say, here's my query shape, electrostatic profile, and pharmacophoric interactions, and sample ligands that will achieve those. And this is the kind of thing that you could do with a virtual screen, but you'd be highly unlikely to find really strong matches to your query, as we'll see. So mathematically, what we're doing is we're trying to learn a joint distribution over these 4 criteria. So again, in our sort of nomenclature, we've got the three-dimensional molecule, we'll call it X1. We've got sort of the shape representation, the electrostatic representation, and the pharmacophores present in a ligand. And we're learning a joint distribution over those four sort of data types because we want to sample from the conditional distribution where we specify the interactions we want, and it gives us a molecular structure that achieves them. So to do this, we've chosen to explicitly represent each of those aspects. We want to explicitly represent the molecule. That's not so hard. That's pretty well established. It's atom types and points in 3 dimensions. You can attribute them with formal charges. You can also have a bonding matrix. That's all quite standard in 3-dimensional molecular design. We also want to represent the shape explicitly, though. And so shape we can treat as a point cloud. Right? We can take the solvent accessible surface area of a molecule, and we can sample points from that surface and that set of points that represents the shape. We can attribute point charges, understand the potential that's going to be felt at each of those individual points, and assign that as the electrostatic profile. So that's just a point cloud where each point now has a scalar potential it feels. And then for pharmacophores, the way that we represent pharmacophores in the most general sense is as a point in 3-dimensional space, the type of pharmacophore, and a direction. This is one of the sort of interesting things about pharmacophoric representations is that they're directional. So there's some non-directional ones like, oh, you've got a little hydrophobic thing over here. But if you're thinking about hydrogen bonds donating or accepting ability, you need to understand the direction that you're pointing. And for aromatic interactions like pi-pi stacking, you have to understand the sort of where is the plane of that aromatic ring. And so these pharmacophores we represent as points, types, and directions. Now to sort of introduce then the actual model that's going to be learning these things, I want to sort of take a slight sidestep to talk a little bit about the architecture that we're using, because we're going to build this off of denoising diffusion probabilistic models. I know that the crowd here leans AI. This might be very familiar, but it might not be familiar to everybody. And so the basic premise of these denoising diffusion models is that we can have a set of data that we can easily sample from a training set, so like a set of images, let's say. We can trivially sample Gaussian noise, and we can add it to the image to corrupt it. And then we train the model, essentially, to remove the noise, such that during inference, we can sample pure noise, and the model will learn how to map that distribution then to distributions of realistic images of faces, in this case. And the basic idea of denoising diffusion is really change the way that people think about generative design. It's been extended, of course, to molecular structures. As most things in machine learning, there's a pretty small lag between an approach coming out and people thinking about how it applies to molecules. So in the molecular space, right, our version of pure noise, right, the static image is just a ball of atoms with random types around the origin. And as we denoise it, we create these sort of realistic looking molecular structures that could have been sampled from databases like PubChem, Zinc, et cetera. So that's the sort of denoising that applies to molecular structure.
Are you saying you're generating random noise in order to come up with some structures?
So in the way that we train this, if you just want to sample molecules sort of unconditionally, you would have pure noise, and then you would denoise them into a molecular structure that looks like it came from the distribution of your training data. That's the unconditional generation. The conditional generation part is where it gets more interesting for us. So in the image world, right, this is known as in-painting, right? This is how Photoshop will magically, remove background people now in your images. Phones do that too. With in-painting, what we can do is we can condition generation on part of our data sample. So we can specify, I would like my diffusion model to essentially invent or impute what could go in this masked region, but I can hold constants part of my sample, right? And so the image will happily generate many diverse samples from the masked part while preserving what you've specified, in this case, on the periphery. As you can see, there's a wide range of things the model comes up with in this case to sort of expand around the central green from a bowl of fruit into a lot of things that are certainly not bowls of fruit, but they've sort of respected this conditioning and they've invented now new images that follow it. So what does this have to do with molecules? So in our case, we're learning the joint distribution over molecular structure, shape, electrostatics, and interactions. So one image for us is that coupled set of 4 objects. And so when we think about inpainting, the part that we specify is going to be the shape, electrostatic profile, as well as pharmacophores. And the part that we ask the model to invent for us, right, to generate through denoising diffusion, is the molecular structure. And with analogy to the inpainting scenario, right, that means that the model is going to be coming up with a 3-dimensional molecular structure that it believes is consistent with this shape profile, interaction profile, et cetera. And so this is how we think about using sort of inpainting for conditional molecular design, where we're conditioning on the kinds of interactions it achieves. We train this as a traditional, denoising model. The machine learning architecture or the training protocol is nothing different from what's established in the literature in other fields. For the actual model itself, because this is a joint distribution that we're learning, we need these explicit representations of each of these aspects. We'll embed them with a model based on Equiformer V2, equivariant neural network. We will then sort of learn to predict the denoising steps. And we can train it on ligands that we just generate from databases, and we sample their geometries and we generate their pharmacophores. And then we apply it again using inpainting to do conditional generation. The point here is that we can teach it about the consistency between structure, shape, interactions, and then generate new structures to achieve target interactions through inpainting. There's a few applications that we showed in the original paper here. The first was just hit expansion, basically. So we can look in the PDB, we can grab co-crystals, we can pull the ligands from those co-crystals, we can re-optimize their geometry so that we don't know the bound pose, we just know this is a ligand that was active. We can generate conformations of that ligand. We can generate its pharmacophoric profile with cheminformatics tools. We can then sample novel molecular structures that can recapitulate those interactions. We take those new structures, we redock them, and we confirm that they recapitulate the kinds of interactions that we see, at least in docking simulations. So with no knowledge of the protein pocket, right, Shepard can do this sort of ligand hopping exercise or scaffold hopping exercise to find very chemically distinct structures that share the important interactions that drive engagement with the protein, but from a sort of development perspective, might give you diverse enough chemical series that if one series had some certain liability in a drug-likeness sense, another series might not. So this hit diversification workflow is something that this model is very naturally tuned for.
So do you specifically like model similarity here in terms of to the reference molecule?
So the reference molecule is what we use to sort of define the interaction profile that we want. And then it's just a matter of using that interaction profile during inpainting to then sample new chemical structures. We could, but we don't do like a second sort of rescoring step based on similarity. But we take the reference, we throw away the graph structure of the reference, but we keep its interaction profile and then it paints. Another application of this is sort of quite useful for turns out to be fragment-based drug design. Right? So fragment-based drug design, the typical workflow would be take a protein crystal, soak it with small fragments, get the structures, learn how those individual small fragments engage with different residues in different pockets. You look for ligandable sites. And then typically, the way that you would follow up on that is to look at the structures that are bound in the protein and think, how can I connect them? And you sort of think about how do I link these different fragments to come up with a new ligand? What Shepard helps us do is say, I don't really need those exact fragment structures in my ligands. Well, I want to use them to learn about the interactions. And so we can extract out just the information about the interactions, or how do these fragments engage? We get that profile, and again, that profile then becomes what we use to condition generation. And so we can use fragment-based data, extract out the profile, condition generation, and then find new ligands based on that fragment screen that will sort of recapitulate the interactions of fragments and ultimately, hopefully give us a good, well-balanced molecule. And so really like in the stress tests sort of example here, we're also thinking, well, what about really complex natural products. Complex natural products have really interesting biological activity. Right? They exhibit a wide range of functions. They're really interesting to work with and seeds of inspiration for a lot of drug discovery efforts, but they're really inconvenient to work with. Because of their synthetic complexity, they're tricky to do SAR studies around. And so what we could do is we can think about taking a natural product and understand, okay, can I just look at the interactions it might be exhibiting, and can I generate now these analogs that recapitulate the interactions it exhibits, but do so with a chemical graph or chemical structure that is a lot simpler to work with. And that's sort of the premise behind this natural product analoging that I'd say is still very much a work in progress, because there's of course a lot of complexity in a natural product that you can't necessarily recapitulate with a single small organic molecule. But this motivation of trying to take these complex natural product structures and come up with analogs that are smaller and easier to work with is also something that ties in really well to the other threads that we're going to cover for the rest of the talk on how we incorporate considerations of synthesis into our generative models. And we actually started this years before, after sort of getting frustrated with the failure modes of generative models, that they come up with ideas that can be very creative in a productive way, but are often very creative in an unproductive way. So the structures on the slide show a range of different reasonableness values. Some of these structures look quite plausible. You might be able to make that and test it. Many of these structures look fairly nonsensical. Right? These are structures that are proposed very earnestly by deep generative approaches, and also non-machine learning based generative approaches. And so you end up with these really bizarre motifs that don't make any sense. These are not things that you would ever actually try to make, have any reasonable way of trying to make. And yet they're syntactically valid, RD-kit will parse them, and so sort of easy to overlook that these are truly non-useful molecules coming out of these models. So we wanted to address this failure mode in trying to teach generative models about chemical synthesis. Now, one approach to doing this is just come up with heuristics that push you away from these weird structures, because heuristics can help. There's a number of different synthetic complexity heuristics or structural complexity heuristics. And so you can imagine that when you ask these generative techniques to invent new structures, you simply bias them with some notion of synthesizability from a heuristic, and that does help. Depending on the different architectures that you're using, you can also fundamentally change the way that you're doing the optimization, and that's what reinvent does. Reinvent is a language model that generates file strings, and it sort of tethers its predictions to a prior. And so essentially it says, please optimize for some property, but don't forget what normal molecules look like, right? Don't forget you've been trained on PubChem. This is what a reasonable structure should be. And so it makes sure that you don't optimize properties at the expense of chemical reasonableness of outputs. Another approach that we've worked on a bit is, can we use synthesis planning tools to take the designs from these models and understand, are they synthetically tractable? How would we make them? And we spent a lot of time in the group also developing open source synthesis planning software that can do this. In a high throughput way, you can assess rapidly, given a structure, do we think there's a straightforward synthetic pathway to produce it? And that sort of touches on a lot of our work in the synthetic organic chemistry space. But the issue with the filter is that sometimes your filter doesn't let anything through. And so we think a better way of approaching this is to embed constraints into our generative models. The traditional way of proposing new molecular structures is, again, to repurpose language models and do this as text. So use smile strings as the basis of generation, or generate graph structures atom by atom, or generate three-dimensional molecules, maybe atom by atom, maybe fragment by fragment, as we did. What we can do instead is we can reformulate the generative task that we are not proposing molecules by thinking in structure space, but we're proposing molecules by thinking in synthesis space or procedure space. So the idea is that if we want our molecular structures to be associated with a synthetic preparation, let's just generate that synthetic preparation in the first place. It will implicitly define the chemical structure that we're making. We can score that set of properties. But from the model's perspective, what it generates is going to be now a synthetic route to access that molecule. And so sort of one of the early instantiations of this, we trained a policy network that would compose this synthetic tree by making a series of decisions about this sort of growing graph of connections. So it would add nodes, it would expand, add reactions. And we constrained the choices made by this agents to commercially available building blocks and a finite vocabulary of reaction rules. And so we wrote down about 100 reaction types. We gave it access to about 100,000 commercial starting materials. And this agent would learn then to select viable molecules and virtually react them together to produce new molecules of interest. So after training it on known molecules with known synthetic pathways, we can then wrap the whole thing in a model-free optimization loop like a genetic algorithm. Change a conditional input, that gives us a different set of decisions, which is a new synthetic route. That gives us a new molecule, that gives us new properties, and then we can iterate. And so the effect of constraining our model to these synthetically tractable structures is that we end up with suggestions that are far smaller and simpler than unconstrained models. This particular sort of heuristic objective, many models have a tendency of proposing really large brick dust kind of structures because we're forcing the model to only propose synthetically accessible ones and ends up with a really simple one-step synthesis to make something that scores about as high as the others, again, according to this heuristic.
You describe this as a policy learning problem.
Yeah.
I'm just wondering, do you have a way to evaluate the different trajectories? And if so, can you tell us a little bit more about like what that value function looks like?
Yeah, so we don't train it as a policy as you would with like reinforcement learning. We train it essentially as like an autoencoder, like a heteroencoder, I guess. Yeah, we encode the molecule and then we decode the known synthetic pathway as a deterministic series of choices. We don't have any intermediate rewards along the way as far as the trajectory goes. We simply train it to, at every step, choose the correct next decision according to our data.
But you show these trees.
Yeah.
I'm just wondering, how do these trees get pruned?
So each tree is a synthetic route to make a molecule. So for one sort of generative episode, we don't prune the tree.
Okay.
So it's sort of just stitching bottom up like building block A, B, let's react them together, and then iterating forward.
Oh,
We don't prune during this process.
Okay.
Yeah.
Okay. Those are reactants.
Yes, right. Squares are reactants, and the circles, yes, are the product of reactions formed by the joints. Yeah.
Thank you.
So this model was I think a good demonstration of how you can embed these constraints, but it was fairly clunky. Again, I know I used that word before to talk about the first model, but tree generation trained in this way was also fairly clunky. So instead of generating trees, which is somewhat complicated, we wanted to make sure that we could force this into the paradigm of sequence generation because models are fantastic at sequence generation.
So just a question, can you go to the last slide page? Are you using this molecule as a negative example or positive example right here? Because that molecule really looks very complicated and difficult to synthesize to me.
Yeah, so the this bottom series is the one on the left is the one that we are proposing. Sorry, I'm ambiguous about that. So this model is proposing this very small, simple structure. The sort of other three suggestions here are unconstrained generative models that are not thinking about synthesis. Yeah. So none of these are good, really bioactive molecules, but according to this oracle, right, the one on the left scores just as highly, and so all things equal, you'd be better off choosing the small, simple, synthesizable one compared to the rest. Yeah. Now, so tree generation can be tricky depending on how it's proposed, and so in this sort of extension of the work, the sort of insight here was to flatten the trees into sequences using postfix notation. So we can represent chemical pathways the same way that you'd represent programs or calculations or computational graphs. We can use postfix notation to sort of serialize then the generation of these operands, which are building blocks, and operators, which are reactions. And so now we can cast the problem of synthetic tree generation into a sequence generative task, which means we can use really robust, scalable transformers to propose them for us. And so sort of most recent model, we train as an encoder decoder, so it encodes a molecular structure, and it decodes then a synthetic pathway to produce it. We use known molecules with known synthetic pathways during training, and the sequence can be sort of expanded back out into a synthetic tree. We constrain this in the same way as before. So we only allow it to select commercially available building blocks, and we only allow it to select the sort of finite vocabulary of reaction types that we constrain it to. Now, we train this, like I said, on known molecules with known pathways that abide by those constraints. But there's something fun that happens as a byproduct of that, which is during inference time, you could query it, you could input a molecule that is not synthetically accessible. And the decoder is going to be forced to try, right, to get as close as possible to that encoded non-synthesizable structure. And so what's happening here is effectively a projection, in a qualitative sense at least, from sort of the full chemical space to the subspace, or the manifold of synthetically tractable molecular structures. So, a subset of chemical space is accessible to the model, and you can feed in any molecular structure you want, and it's going to decode a synthetic pathway that tries to reconstruct that molecule, but it might make a mistake, or might try as hard as it can, but we've constrained it so that it's not able to. What that lets us do is actually clean up some of those silly looking structures that other models are likely to produce. So some SMILES genetic algorithms love to put boron where it doesn't belong. And so we can take those structures and we can clean them up. We can project them onto the synthetically accessible manifold of things we know how to make. We can take this highly constrained ring and we can expand it into a pretty reasonable tetrasol that we know how to make this whole structure. Because again, this model proposes structures as their synthetic pathways. So I'm showing molecules, but really we have the full recipes to produce them. We've sort of observed empirically that this projection, in many cases, tends to be property preserving, the first approximation. So I'm showing some of the scores. These are from heuristics, so I would not really give them much credence. But for example, in this bottom left case, we've got a particular ligand that docks with a Venus score of negative 11-ish. With a 7-membered ring, this was not part of the building block vocabulary. And so when the model projected this onto what it knows how to make, it shrunk it down to a 6-membered ring, and it docked about the same. Right? Sometimes that's not always the case, but the idea is that we can use this model for de novo generative design, but also for cleanup. Cleanup too is something we can apply to those structure-based models. So structure-based models can invent hypothetical ligands with no guarantee of synthetic tractability. But if we take those generated ligands from those other 3D models and we round trip them through ours, we can find synthetically tractable analogs that approximately preserve the poses and the engagement with the protein. And this, again, is sort of an empirical result that for now is validated just by docking as the oracle.
So it says empirical. I mean, are you thinking of combining the approach like you can add pharmacophore constraints?
Yes. Yes. Yeah. So part of the idea would be we want to design the best ligands we can with full consideration of interactions, but then we want to sort of pull it towards the synthetically accessible manifold so that it's actually possible to, well, it's possible on an academic budget to synthesize and test. We need them to be synthetically simple structures. So we're trying to combine these workflows at least as like a sequential generates and then project step, but maybe sort of more intimately as well.
What's the name of this tool again?
This one is, we called it SynFormer. SynFormer.
And Connor, when you're saying synthetically tractable,
Yes.
did you set a limit, like so many steps or something like that?
We don't set an explicit limit, but practically it's like 5 steps. So during training, we stochastically generate hypothetical products, and that sampling, we don't go too much longer, usually like 5-step pathways. And I should say that the building blocks are commercial ones, that's easy. The templates, we re-implement the ones that IIDAI uses for their IIDAI reel. So they very kindly shared a PDF of the templates with us, not the smart strings, but a PDF of the schemes. And so we just wrote those up as smarts patterns. And so our chemical space is trying to be about the same as IIDAI reel effectively, but potentially with more reaction steps and in a broader set of building blocks.
So this is great, by the way. This was much needed, and this is very elegant. It is very satisfying to see. So thank you. Did you take one of those 3 gigantic molecules and find what was the closest neighbor?
No, no, we didn't. Yeah, no, so we did not do that. It's definitely the case that if you're too far from, like you don't preserve properties at all. Like so if you start too far away, you're out of luck. So we've only worked with things where it's sort of minor revisions to the structure.
That's really useful.
That's usually the case. So
Yeah.
it's very
We started with the analogy of in painting
Yeah.
for the diffusion model. So you had these different sort of views of the molecule that you wanted to sort of optimize and
Yeah.
sample from some degenerate set of formulae. But then you added a transformer-based model, not a diffusion model that is sequence optimal, trying to learn the grammar of chemical reagents. I maybe I missed it. How do they get combined? These two architectures.
Yeah, so in a practical sense,
Yeah.
we could do this ligand-based 3D design with consideration of interactions and generate a ligand in 3 dimensions. We could then map it simply to a spinal string that we would use to round trip it through this, because this synthesis constraint.
Yeah.
It's a workflow. It's not truly like a end-to-end model. It's a workflow that would stitch the two together for now. Yeah.
I have a question on the practical recyclability, but
Yeah.
like you're using enamine building blocks, right?
Yeah.
They have like a success rate of like 80% or something like
Yes.
that. So as you combine these multiple steps,
Yeah.
The
Yes.
probability actually goes down.
Yes. So the guarantee of synthesizability is subject to the fidelity of the templates, which are not perfect. We inherit the same sort of failure modes as any make-on-demand virtual library from this. Yeah. So, or separate to this, and there's also lots of work at IBM on this, we can build different data-driven tools to try to refine the prediction of which reactions are feasible or not, that are a little bit more nuanced than templates. That could be layered on top of this if you wanted to have an extra step in the workflow of down selecting or filtering the pathways. But the connection here, and we can do the expansion stuff too, but the connection to the make-on-demand libraries is intentional in a sense. Because these libraries are constructed through constraints that are highly practical, right? That's why it's amazingly convenient just to order molecules from a CRO and not have to worry about a custom synthesis. So we want to inherit that benefit, but we don't want to enumerate billions or trillions of molecules and then search it in a virtual screen. And so essentially this generative model that is synthetically constrained using the same principles as a make-on-demand library simply learns how to navigate these too large to enumerate chemical spaces, but in a way that sort of lets it do it iteratively, right? So it can choose which parts of the space are more relevant. And so we don't have this massive storage or memory footprint of a large enumerated space. We can simply define it implicitly. And then the sort of chemical space as defined by the building blocks and the templates up to, X reaction steps is accessible to this compact generative model to explore.
I guess my question is like, if you restrict it to, let's say, one part, like one step.
Yeah.
How well is the property preserved? Is it possible to do that?
Yeah, so if you impose constraints and you only want to do one-step syntheses, then you definitely will sacrifice your ability to cover maybe the range of functions you want to cover. We haven't done a lot of explicit testing about that empirically, but I will say, like, I really, one of the things that I'm excited about for this is the ability to impose your own kinds of constraints, like step counts. You could also say, I don't really want to do 100 reaction types, right? I don't know if folks from Zurich are signed in, right? But if you constrain your reaction vocabulary to the things that are compatible with automation, then all of a sudden you have a generative model that can navigate chemical space that is accessible to your platform with your in-stock building blocks and your transformation rules that define, hardware compatible steps. And so I think this is simply just a way to take an enumerative paradigm of enumeration and just make it generative without giving up the benefits of having these kinds of symbolic constraints. Yeah, that's the intention. So that takes us to the end. So I really wanted to focus on those two big threads and how we're thinking about sort of revisiting or revising generative approaches. So we do still think a lot about virtual screening again because it's highly practical. But in the generative space, what we're trying to do is infuse understanding of non-covalent interactions in so that the ligands we generate do exhibit those good selective interactions with target proteins. And then that does not address then the sort of other consideration of synthesis, but of course we can have these constrained models that are heavily based on the principles for make-on-demand libraries. They inherit their benefits, they inherit their failure modes, But I think in combination, this is really helping us make these tools, I think, a bit more practical. And hopefully we'll see some more prospective use within the group and outside of the group on these. So I'll close there. Thanks again for sharing this and for folks online for tuning in. Of course, all of the work that I presented was actually not my results. The results of very talented students and postdocs in the group. And so obviously this reflects their hard work as well. So thanks very much.
Thank you. So maybe we should take some questions from Zoom, since obviously we've had a lot of from questions. Can I hear it? Are there any questions from Zoom? If there's not, then perhaps we'll have a question here. Any more questions?
Can you comment on like, maybe 4D? In other words, if there's a, an in-painting problem that says, create a face that's consistent with a smile and a frown, then that's easy with faces, right? Our musculature can do both, but the same is true for molecules, right? You can create a formula that's consistent with two different geometries.
Yeah. So in the current Shepherd, we have a rigid interaction profile and a rigid shape that we use for conditioning. That is how we would think about flexibility. The first step to think about flexibility would be, let's say, conformational ensemble of the query, right? And maybe be in painter condition on like the full ensemble of many different conformations where, again, the chemical structure is shared across conformations of that ensemble. Doing that, I guess, like naively for now, it would be difficult in terms of the scalability of doing this. It's a little bit expensive using these point cloud representations to have a good density of sampling and using the equivariant architecture, surely non-equivariant ways of doing some of this. But yes, that would be the thought, is that's to condition on the ensemble of conformations and the corresponding profiles, not just the rigid snapshot of one.
Ask a follow-up question. In the painting things, you say you fix some of the characteristics which should be kind of the background, what is not you want to generate, like which is your structure. Between the characteristics that you fix, which is weighted the most? They're equally weighted, which is contributing the most toward the structure? Or you play with different.
So one could weight them. We don't sort of explicitly try to prioritize one over the other. I'll say empirically, it is harder. Empirically, I think it's pharmacophore specification is a much more specific thing than just the shape or electrostatic profile. So if you imagine a function that goes from electrostatic profile to molecule, that's like a one-to-many kind of mapping. Depending on how you specify your pharmacophores, that sort of constrains the space more, and so it's harder to satisfy that exactly while being chemically diverse. And so we find the way that we currently assess consistency, the pharmacophores match the least well, but that's sort of based on how we've defined them. They're the hardest ones to recapitulate. And so maybe playing around empirically with the weighting factor given to that could help, but in principle, they're all sort of weighted equally in this big joint representation.
I want to pick your brains on what are your thoughts on lead optimization? Because for lead finding and hit finding, if we do brute force, we will get somewhere anyways. But for lead optimization, even the most accurate methods out there, regardless if it is physical or AI, they struggle because you want the accuracy to be around or below 1 kcal per mole, and there are just aren't that many methods out there that even close to that. So what do you think that we can do?
So we are, for now, casual users of structure-based methods. And so we are not sort of really pushing the envelope on the fidelity of like structure-based scoring oracles and free energy calculations and really trying to find workflows to push potency right as far as you can. I'd say that the where a lot of these tools are most useful. Okay, well, if you did have that oracle, these would be very useful for optimizing that. But given that you don't, I think that where these tools land is slightly earlier in the pipeline. You know, typically like one of the applications of Shepherd that's quite interesting again is this ability to generate chemically diverse structures that still recapitulates a known set of interactions. And so if you did run into, you know, specific AdMet sort of liabilities, right, you can potentially optimize around them by hopping over to a different series. But we don't have, we don't have that sort of structure-based oracles that really give us binding estimates, you know, with a fidelity you could trust.
Do you foresee that we're getting close to that stage?
I think there's a lot of people working on it, and so I do think it will improve a lot. Yes, how fast and how abruptly, I'm not sure, but I do expect that it will improve quite a lot.
In terms of failure points, what are the classes of ligands that either Shepherd or Lumber don't? There's some like systemic properties about these ligands that make it difficult.
Yeah, so they're interesting models in the sense that the training data we can generate as much training data as we care to. So in some ways, the limitations of Shepherd would be the chemical spaces that we've used for training to show it these interaction profiles of different motifs. So if there's a certain substructure motif or certain type of pharmacophore that we've excluded, it's not going to know about it. If we train it on small structures, it's going to be predisposed to generate small structures. If we had trained it on natural products, then when we used it to analog, we probably would have ended up with something that's closer to a natural product. So it's more just like, what is the distribution on which we train these that is most limiting. Yeah.
Let's all thank Connor again. Thank you, Connor.